How many people here at some point in their lives have thought it'd be really cool to build something that goes into space? Yes. Okay. And I know there are a few in the room. How many of you have built something that has or will go into space? Yeah, there are a few. Yeah, there isn't a big enough catapult to launch me. Okay, so for a lot of people it seems like a crazy dream and something that's unachievable. And for a long time it's been really, really difficult to, at a hobbyist level, build anything that ends up in orbit or does anything meaningful in space. One thing that was done a while ago to address that was publication of the CubeSat standard. This originated in 1989 in Cal Poly, and the idea was to have a standard platform or a standard structure that could be used for building picosatellites. And the basic standard says it's got to be a 10 centimetre cube, must be under 1.33 kilos in mass, and there are a number of other things as well. So it has to have deployment in locks, and there are some other regulations. But the idea is to try to standardise on a very small platform which is relatively cheap to produce. And one of the ways that's done is by having a very well-defined chassis. So this is a typical commercial off-the-shelf CubeSat chassis, and it's a bit of folded aluminium. I'm slightly understating it there, but a chassis like that, unfortunately, is still worth something in the region of $5,000 to $7,000. So the cost of putting up a CubeSat, it's in the region of $65,000 to $80,000 to get a little cube into orbit. And typically about half of that is the launch cost, so it's in the order of $30,000 to get a kilo into orbit, and about half of that will be the mechanicals and the electronics and all of the actual hardware itself. So it's way cheaper than most commercial satellite projects, but 60 to 80 grand is still a lot of money. It's not the sort of thing you do at a high school science class. Now, the way these are launched is using a device called a P-pod, which is a polypicosatellite orbital deployer, which is basically a fancy name for a box with a spring in it. The P-pod is designed to hold up to 3 satellites. When I said that a satellite is a 10 centimetre cube, that is considered to be one unit, so it's a single unit of a CubeSat. And just to give you a sense of scale, this is the size essentially of a 2U. So this is like 2 cubes. You can have CubeSats that are either 1U, 2U or 3U. So if you have a 3U CubeSat, it fills the entire P-pod. Because P-pods are standardized, they can hold multiple satellites. And the idea is that these can go up as a secondary payload on a launch for a commercial mission. If there's some commercial satellite going up and the satellite might weigh a ton or several tons, there's typically a bit of spare payload space. And the idea is that multiple P-pods can be mounted in the launch vehicle such that the secondary payload of the CubeSats can be deployed at some point. There is a little solenoid that allows the door to open. The spring pushes the CubeSats out. Typically, the CubeSat chassis have little separation springs in them as well. So as they come out, they separate from each other. And it's a very low-cost way of getting something small into orbit when you can't necessarily justify a launch just to get a kilo up there. That's the way it was done for quite a few years. Many CubeSats have been launched. Just recently, there has been a new deployment method, which is what's going to be used for ArduSat. This is a picture of the HTV-2 mission, which is using a Konotori vehicle. This is a JAXA mission, so Japanese Space Agency. The Konotori has 2 payload compartments, one of which is sealed and is accessible from inside the International Space Station once it's docked, and one which is open. What you can see there is the arm, or the Canadian manipulator, reaching into the open to space section of HTV-2 so that it can retrieve a payload. What it can then do is transfer that payload without it passing through the space station to the airlock of the Kaibo module, which is the Japanese experiment module. So what you can see there is sorry, I can't pronounce his name, Hoshida, who is the flight engineer for Expedition 33. And what he's working on there is a deployment of 5 CubeSats that took place on October 4th, so just a couple of months ago. What you can see are two pea pods. Those are you can just see the square ends of them, and they're on a little sled. And the actual sled itself can be taken outside, so it can be prepped from within the airlock, and things like remove before flight tags removed, and you make sure that all of the payloads are ready to go. Then it can be taken outside of the airlock by the arm and deployed again. So the process looks something like this. So the airlock opens up, there is the sled, which is the SSOD, so the Small Satellite Orbital Deployer. That contains multiple P pods. The arm then takes the sled out, and the solenoid allows the satellites to be released. So I've heard this described essentially as sending them to the International Space Station and throwing them out the window. So that's pretty much what happens. Now, on this particular launch on October 4th, this is a photo of 3 of the 5 satellites passing in front of the solar array of the ISS, which is a really cool photo. First time I saw this photo, I thought it was well, you can't really see it very well on the projector, but it's so amazingly crystal sharp that I thought it was just a 3D render. I thought, this is fake, but it is actually the real thing. The satellite you can see up in the top right is called FitSat-1, which is this little thing. Came from Fukuoka Institute of Technology, and I think this is quite interesting because the official mission of this satellite is to investigate methodologies for optical communications with satellites. Now, you see those things on the top? Those are high-intensity LEDs. This is basically a big blinking LED in space. The purpose of this is to flash out messages in Morse code as it travels through the sky. So I thought that was very cool. But that cost them $80,000 to put a blinking LED in space. So if you are wanting to get some kind of an experiment in orbit, and you don't want to cough up $80,000, how do you do it? And how do you take access to this sort of platform down to a very low level, ideally so that science classes and hobbyists and individuals can get involved as well? And that's where the ArduSat project comes in. So it was funded on Kickstarter. The project goal was to raise $35,000. I think it exceeded that within about 20 hours. And the funding goal was on the basis of the minimum funding required to build a basic CubeSat platform and then basically hitch a ride, obtain a free launch with someone willing to take the satellite up and put it into orbit. So as you can see, it well exceeded its funding expectations. And I saw this on Kickstarter and I thought, space, Arduino, this is awesome, I've got to get involved. So I sent them an email and said, this is so cool, can I help you in some way? I'll make your hardware for you, whatever. And they said, yeah, sure, actually, we've got your book and we use it for reference. So I knew they were in trouble at that point. At the point that I got involved, there was the general concept of building a multi-experiment platform that could be used by many people simultaneously, and the purpose of the mission could change over the duration of the flight. So they had some 3D models that were used in the Kickstarter project. They had a general architecture concept, but it was still quite early stages. The team that put this together was a group of 4 people who all have experience with space projects through various agencies, and they met while doing a master's class at International Space University. I think it was only in 2011 or so, and got together and said, let's do this. So the person I've been dealing with most is Jeroen Kappert, who's, you can see up in the top right there. He's the lead payload engineer. He's primarily a mechanical engineer, so he's done all of the work on the physical structure and how it all fits together. Now the objective, the mission profile, or what this is, the way this will work is the platform itself will go into orbit. Like all CubeSats, it'll have a very limited lifetime. If we're lucky, it'll stay up there for 6 months. Worst case, it may stay up for a few weeks, but it's going to be probably a few months duration that it will be in orbit. The platform itself is designed with multiple sensors and a suite of processors which can all access those sensors. So the idea is that if you can come up with an idea for an experiment that can run on this platform, your code can be executed on one of the processor nodes, access the sensors, the data is stored, and then sent back down to you. And if you take, say, a dozen experiments running in parallel, and they are running for about a week each, and then new code is uploaded to the satellite to run another experiment for another group, what this means is that by amortizing the cost of this over a number of experiments, their objective is to have a platform that will allow you to run an experiment in space for a week for in the order of $300. So I think this is a really good objective. The idea is that if you're a science class and you had an idea for an experiment, you could raise $10 per student and you could buy yourself a week of satellite time. So it's a really cool objective. And so I got really excited when I saw this and I just wanted to get involved. So at the point that I got involved, they had this as their architecture diagram and they had this as their bench test. So it was a bunch of off-the-shelf breakout boards for different sensors. As you can see, they are off-the-shelf Arduinos. So there are, on that stack you can see some Unos, Leonardos, there's an Arduino Ethernet, some other bits and pieces. This particular experiment is testing a shared I2C bus. So in this case, all of those boards are on the same bus and they're all talking to the same sensors. So they had the basic concept, proof of concept, but it really needed to go a lot further in order to get it to being flight ready status. So the actual ArduSat 1 stack is going to be, for the most part, very similar to other CubeSats. With the exception of the bottom line, that's pretty much the same. Most CubeSats have some standard parts. There is the flight computer, which maintains attitude control and overall management of the satellite. The electrical power system, which includes the solar cells, batteries, charge management, distribution of power, monitoring power consumption. There is a radio, so there's got to be some communication with the satellite, and the chassis. Now, all of those parts are commercial off-the-shelf parts, which means that the base hardware cost of building something like ArduSat is still in the close to $30,000 region just for those parts alone. And then there is the payload. Now, one thing that's worth mentioning here is that for a single unit CubeSat, because you have all of this fixed infrastructure, you can't do without batteries, you can't do without a radio, etc. Those things alone take up about 2/3 of the volume of the little cube that you have. So you end up with only 1/3 of one of these cubes for your actual payload to do anything useful with. And that's the mission-specific part of the satellite. So you have to fit a lot in. One of the things to keep in mind, though, is that because that volume is relatively fixed, if you go for a 2U satellite, you may have slightly higher power requirements, but for the most part, the fixed infrastructure is still the same volume. You end up with about 4 times the payload volume for double the size. So you get economy of scale basically building slightly bigger satellites. For ArduSat 1, because this is still largely experimental, it's being done as a single unit satellite. So the payload itself, that's the bit that is really interesting at this point because the rest is just commercial off the shelf. There will be experiment processor nodes. Now the objective here is to build an architecture that is as simple as possible to replicate for hobbyists or students. In this sort of situation, it would be usual to go for an MCU that is much more optimized for the particular experiment. But it was a deliberate decision to go for ATmega 328s, which is what's on an Arduino Uno or one of the common Arduino models. Because the idea is that you should be able to walk down to your local shops, buy an off-the-shelf Arduino, some breakout boards, get some sensors, plug it together, and replicate at least part of the architecture, download the IDE. You can compile using AVR GCC, so open source software stack, and at home or in your classroom, prototype the experiment as closely as possible to mimic the architecture of the satellite. So apart from the processor nodes, and when they approached me and started talking to me about this, they said in their mind they were hoping to fit 10 processor nodes in. So the budgeting was based around running 10 experiments in parallel. And so we've fitted a few more than that in, which you'll see in a moment. There's also a supervisor node. Something needs to coordinate all of these Arduinos. And each Arduino within the payload, it really thinks it's an Arduino. It's running the bootloader. It's got serial comms on it. As far as it knows, it's a regular board just sitting there running on your bench. So the supervisor takes the role of the IDE, and there is multiplexed serial comms to each of the nodes. The supervisor can control power to each of the nodes and shut them down, load new sketches into them, etc. And it also provides some mass storage. So there are 23 sensors and 3 cameras in the payload as well, which is pretty impressive, fitting it in a tiny little space like that. And as I said, they use I2C as a common bus between them. So there are a bunch of sensors, a magnetometer. Probably the most interesting one there is the spectrometer. This is a project called Spectruino, which is an open hardware spectrometer project. And this is going to be one of the first projects to use Spectruino. So the ArduSat team over in the US have one of the prototype Spectruinos that they are using for their testing. And that'll allow a whole lot of different, different fun experiments to be done. Oh, GPS as well. GPS is painful in space. Yes, there's a question here.
Are you using the FU 6000, 6000 or something else?
I don't know.
Okay. Just be aware that the rotation rate of satellites in orbit is quite low and goes to the COTS fixed stop. INUs can't track the low rotation rates. You might be able to get another solution to that.
Yep.
Swamp through the noise.
Swamped in the noise? Yeah. Okay. Now, the question of GPS raises 4 letters that are very fond to me, and I'm sure many other people here, which is ITAR. Yes, Bidar loves those guys. So ITAR stands for...
I can't tell you about my CubeSat project.
Exactly. So ITAR is international traffic in arms regulations, and it is legislation in the US which prevents American companies from disclosing designs or selling to other countries. So the result is that GPS obviously is US originated, and there are all sorts of things built into it to specifically prevent it being used for things like guiding missiles. So if you go and buy a GPS module and you try to make it go above a certain altitude or fly faster than a certain speed, it just goes, I'm not allowed to do this, and it turns off. If you're in a satellite traveling at 14,000 kilometers an hour, you're slightly over that limit. So there are some interesting things with things like space-rated GPS, and there are all sorts of, there's red tape around it. For example, you have to get special clearance to obtain one of the modules. It has to be tracked, like they have to know, it's basically like a chain of evidence. You have to sign for it, and you have to prove that it's either been destroyed or returned at the end of the experiment, etc. And they're worth ridiculous amounts of money, like $15,000, $20,000 sort of ballpark. So when I started on the design for the hardware, the obvious use case is the satellite itself. But that's really only a little part of the puzzle. There are a whole lot of different use cases for the hardware that's associated with this project. First is satellite platform development. So that's initially doing ground testing and just integration of sensors and all of the other things that you want to do, proof of concept sort of stuff. Then there is experiment development, and this might be performed by anyone, anywhere around the world, not just the ArduSat team. So the idea is to make this hardware accessible to anybody that wants it. Obviously there's the ArduSat-1 spaceflight, so the hardware for that has to be very specifically designed to fulfill that requirement. It has to be made with particular materials that are space rated. Then there are also subsequent and third-party flights. There might be other people that want to use this hardware, and we'll talk about ArduSat-2 and ArduSat-3 in a little while. And non-space applications, which is something that I'll also get to in just a moment, but it was rather unexpected to me, but that's probably one of the coolest things about this. So there are a number of different modules that I started putting together. So I laid out a plan for the different modules I wanted to build. The prototyping module, which is not something that would ever go into space. I'll just go through them. So the prototyping module, it's basically like a prototyping shield for an Arduino, but specifically designed to fit within the CubeSat chassis specification. It has a CubeSat bus breakout, and what you can see on here is the stacking connector on the right-hand side. So the way these work, because one of the standards that was used to derive this was the PC104 industrial computer bus, which uses stacking cards. So the idea is that you can have a chassis with rails that will allow you to stack multiple cards on top, and they use pass-through connectors. So this turns out to be a really useful little thing. And it's got vertical cable clearances. Most signals pass through the stacking bus, but there are things like high current cables for the batteries and solar cells that are usually done on direct point-to-point runs. That's why the board is a strange shape. It's got clearances so you can run cables up beside the stack. Now, I started on this because I just wanted something really simple to make sure that I had the mechanicals right. I didn't want to build something that wasn't going to physically fit in the chassis, and I wanted something that would allow me to just put breakout boards on it and put parts on it and experiment and see how it goes. So I just sat down and designed this and generated the production files and sent them off to our production manager in Beijing and said, these are the particular connectors I need. Now, these are a standard connector that are used in CubeSats, and they come from a supplier in the US. So he looked at the specifications for the connector and got in touch with the US supplier, and then came back to me and said, I could have these custom made for you in a factory in China faster and cheaper than ordering them from the US. So I said, go for it. We had the mechanical specs. So a couple of days later, I had 2 samples from 2 different factories, and we put them through some testing and measured, contact resistance and insertion force and all of those sorts of things, and provided some feedback. And a couple of days after that, we had 1,000 of them for less than the cost of ordering a few from the supplier in the US, and faster than they could have shipped them. So what these allow you to do is just to quickly build things. So this was just one of the little experiments I did early on, just to play around with some sensors. I found with projects like this, the way I like to work is very incremental. I like to just be really tactile and create something and get something working and then iterate from there. So even if none of the initial hardware is actually going to be used in flight, it's a starting point. It gets you going. So what I did was created a module with a few sensors on it. And in fact, it's right here, with a battery pack and a big remove before flight safety interlock. And this has a Leo stick on it, and an RTC, an accelerometer, and a few other bits and pieces. So we'll power that up. And over here, I have an app written in processing. So we have a receiver over here, which is receiving the 2.4 gigahertz signal. And this is accelerometer values that are coming in. So obviously none of this is going to be used in the actual satellite, but this is just something that I put together on the bench because it's a good way to get started. And then I worked up from there, as you'll see in just a second. So beyond a simple breakout board, the next thing I wanted to put together was some way to rapidly build a stack involving an Arduino rather than soldering headers onto a board. So I made an Arduino adapter module, which you can think of as an upside-down shield. Basically, it takes the Arduino headers, they're inverted, so it basically looks like that, and you stick the Arduino in upside down, and you have all the breakouts. You've got all the CubeSat bus broken out, all of the Arduino pins broken out, jumpers for power, there's reset, power indication. So with a few jumpers, you can then put this in a stack with other either flight-ready or just experimental modules and run tests and things on your Arduino. So once again, this is not something for flight. This is just something for the initial, it's a step beyond a breadboard, basically. It's building something that's a bit more robust and that you can have, like this, you can throw it around and it's not going to fall apart. So you can build up little experiments. So as I was doing this, the ArduSat team were concurrently working on some of the sensors. So they put together some tests, and this was a module that went up on a high altitude balloon flight. I think it was around October. And that big funny shaped thing at the top is the spectruino, so that's the spectrometer. You can see a GM tube down in the bottom left with a little red cap on it, and in front of that is a, you can see the transformer for the high tension supply for the GM tube. So once again, this is iterating on the concept and building something that is robust enough to send up on a high altitude balloon flight, get some data and just see what happens. As you can see, there are some very oddly shaped pieces in there. The spectruino itself is an odd shape. It's very hard to get everything to fit around it. And so being a mechanical engineer, Jeroen is crazy about 3D models. So he modeled all of this, and of course you can't have, I think there's a new rule. You're not allowed to have any project that doesn't involve 3D printing. So 3D printing is awesome for checking mechanical clearances. So just for making sure that you've thought about things and you haven't got it messed up in your head. So they went to the trouble of printing some pieces, and this is a model of the satellite. Some of these are fixed, so the models are built from the, you can see down on the bottom left, for example, that's the electrical power system, which is the commercial power system. You can see the two big batteries stuck on it, which I think are 18650 lithium-ion cells. So my job at this point is to take the mechanical constraints of the sensors and build the board that will run all of the experiments and talk to those sensors. Now, in communicating with the ArduSat team, I received a number of design files, including positions of the mounts and how everything would fit together. And it seemed that every time I got a file, all the measurements would be different. And it was doing my head in, so I went really high tech. And one of the problems we had was that the 0 point on the different CAD programs was different. So in Eagle, which I was using for the PCB layout, it was down in the bottom left. And it was in a different position for the 3D models that they were generating. And so I ended up, and also we discovered that there were some conversion errors happening between, would you believe it, imperial and metric. So I ended up with a sheet of paper with all the dimensions written on it, and I took a photo and emailed it to Jeroen and said, is this right? So we agreed on that was what it was. So once I had the mechanical constraints, which are the mounting holes for all of the modules, I then had to translate that into CAD, so I had to design the PCB. So the way I did that was start with the mechanical outline of the board and lay out little modules. So each of these little modules that you can see is essentially an Arduino, but it's about the size of your fingernail, so they're very small. It's using some 0402 parts and really small stuff. But I needed to make that fit around the mounting holes. It would have been really easy if I could have just taken that 16 node grid, moved it sideways and said, there you go, but it wouldn't fit. So I started by laying out some communications channels, just trying to work out how I would get the links to happen between all of the different parts of it. And then once again went super high tech, printed it out about 1.5 times size, and I cut out all of the shapes, and then I just moved them around on the page until I thought, yeah, that's going to clear all the holes. So when I was happy with the layout that I had, taking into consideration that some of the, there are connectors on the bottom of this board, which is where the sensors plug in. And the modules have wires and tracks and things underneath them. So I had to move them so that there weren't any particular wires that were in the wrong place to foul the connectors underneath. And then, of course, just translated that into a layout. So that's where we got to. And I had a bit of a rest after I'd done that. It looks like a crazy mess, but if you break it down, there is a little bit of planning, a bit of design to this. So we'll strip back the layers, working back down towards the bottom of the PCB. So this is the bottom layer of the PCB. It's a 4-layer board, and that's providing a lot of the power interconnects and I2C. The top of the board, obviously, is where the pads are for most of the parts. So you can see there the supervisor processor up in the top right. You can see the multiplexers on the left, which are used for the serial comms, and you can see the position of all the nodes. So one of the issues that I'll talk about in a second is thermal regulation. And so what I tried to do was achieve long runs of copper wherever I could, so that heat from the MCUs would travel either vertically or horizontally. Now within the chassis itself, there is very good thermal conduction through the chassis. So it's a matter of getting the heat out as much as possible, spreading it around the PCB so that it can then go elsewhere. And you can see horizontal runs on the next layer. So the end result is that board there, which is actually right here. So there are two of these in existence right now. This one is here, the other one is in California. And I think right now that's probably about the most powerful Arduino in existence. So you can't take it. So what that has on it is the equivalent of 16 Unos and a Mega. So I used a Mega 2561 MCU. If you've got an Arduino Mega that uses a 2560, the 61 is essentially the same thing with a whole lot of pins missing. And it's about 1/4 the size, but the internal core is the same. So it's essentially a Mega. The supervisor node is not going to be running Arduino code. That will be running free RTOS. The AVR port of that is maintained by Philip Stevens, that some of you may know. He's from Melbourne. And the supervisor itself has control of power of each of the processor nodes. So there are a number of factors here. One is that we may not need all of the processor nodes running at once. The objective was to have 10 of them on the stack, and I managed to fit in 16, which is nice. But you don't want stuff just sitting there burning power. So what I've done is used little solid-state switches to control the power rails to each of those processor nodes. So the supervisor can just power down any of the nodes that it doesn't need at the time. And if we have something like failure of a node, we can isolate it, just power it down, bring the experiment up on another node. There is current sensing on the input to this particular module, so we can see how much power is being used. The supervisor, as I said, uses microSD to store data. And underneath are the headers for the assembly. So, and isolated I2C. This is something that puzzled me for a while. It was one of those problems that I was just sitting there thinking, I don't know how to solve this, until I was having a conversation, I think, in a pizza shop with Andy Gelmy and a couple of other people, and some suggestions that have sparked an idea. One of the problems with I2C is that the way it works is that you go high impedance or you pull the line low to assert it. If you have a node on an I2C bus that powers down, all of a sudden it just asserts the bus and you're screwed. So nothing can talk anymore, which means if we power down one of the experiment nodes, or worse still, if there's a failure of a node and we've got no control over it, you could lose comms for everything. So the whole satellite basically just becomes a bit of space junk, which is not fun. So what I've ended up doing for that is using a technique that's normally used for level shifting between multiple I2C buses. So if you have 3.3 volt and 5 volt devices, you can use a couple of FETs and a couple of resistors to do level shifting. One of the benefits of that is that if you power down a node on one side, like on the node side of the level shifter, it doesn't assert the bus. So we can power down or have any node on the I2C bus fail, and everything else will just keep right on trucking. So I was really worried about this when I first did it, because it's one of those things that I thought, yeah, that solution is too good to be true. But I went out on a limb and did it, and they haven't yelled at me yet. So sometimes you've got to take risks like that. And it's got top and bottom temperature sensors. There are temperature sensors all the way through the structure.
Hey, John.
Bitter.
You mentioned power control, and I get all of that. You've got a lot of AVRs on there doing, I don't think of those as being low power. What's your power budget for this board?
It's in the order of a couple of hundred milliamps.
Jesus. I'd love to have that much for the whole satellite.
Now, there were some mistakes I made. There are several bits of my shame that you can see in this photo. One of the mistakes I made is that the ICSP connections for this particular model of the chip in this package are not on the SPI connections, which pretty much all of the others are in this family. So I ended up routing the wrong connections, and we then couldn't load any firmware on it. And luckily, the correct pins were taken out to the muxes, and they have big handy 0.5mm pitch pads on them. So all I had to do was break out the microscope, and it was easily fixed. The other mistake I made is once I solved that problem, I managed to incorrectly set the fuses for the oscillator settings in the MCU, and all of a sudden it wouldn't talk to me anymore. And I thought, great, I've got like one of these and I've bricked it. So what you can see there is another Arduino compatible board. I set the fuse in that to enable the clock out bit, so it's driving a buffered 16 megahertz signal out of one of its digital outputs. And that is, I had to scratch some tracks on the PCB under the microscope and patch it in, and it's driving the clock signal into the supervisor MCU. And then it talked to me again, and then I was happy. One thing you can't tell from that, I probably shouldn't be embarrassing myself with this, but the other mistake I made was last year when I was designing the Leo stick, the very first version of the PCB that I laid out, I stuffed up the footprint for the little RGB LED and I made it too wide. And right before it went into production, we discovered this, and Mark fixed the footprint and then sent the files off for production. My version of the library still had the old busted footprint in it. So this has the incorrect footprint for the little RGB LED. So every one of those has a little status LED with the wrong footprint. But a bit of hand soldering, microscope, all good. So this gets to the next board, which I was really hoping to have here to show you today, but I haven't had it finished in time. What I was wanting to do as the next stage, as you're experimenting with this sort of thing, like you want this sitting on your workbench, you don't necessarily want a power supply plugged in like a big bench supply. It's really nice to have a little self-contained thing. So I thought, that's easy. What I'm going to do is just get one of these board layouts, and I'm going to put a connector on it for a LiPo cell, and I'll put a voltage regulator on it, and I'll be done in like an hour and produce the boards. And I couldn't help myself, so about a week later, I was still messing around and feature creeping this thing, and I ended up with a design that looked like this. So it includes a wide range, so 2.7 to 40 volt DC input for a solar cell, an intelligent battery charger, and a fuel gauge system, which reports over I2C. It's got multiple output regulators, and of course, if you're going, and top and bottom temperature sensors, because you want to know how hot your batteries are getting or how cold is more to the point. And I wanted to know how much current was being consumed, so I've got current consumption monitoring on the inputs and on the outputs, which means you need an MCU to report it, so I stuck an MCU on there. And if you've got an MCU, you might as well break out some of the pads so that you can get it to do other things. Andy?
About 3 LCAs ago, you promised a battery charger at the end.
I did promise a battery charger at the Arduino MiniConf.
Promise delivered?
Oh, no, I don't have the hardware yet. And I thought this was fantastic. It's great. And so I sent this design off to Jeroen at ArduSat and said, check this out. This could be really useful. It's not just a bench thing. This could potentially become like a flight capable electrical power system. And he looked at it and said, the batteries you've used, you're never going to get those through the certification. So you really have to use this particular cell or this particular cell. So I went, oh, great. Back to the drawing board. And the particular cells that I had to use are a totally different shape. So basically, I just ripped it all up and started again. Ended up with this. So the end result of this is that that little MCU in the bottom right corner is a 32U4, so it's the same as on a Leonardo. And yeah, so the end result is this. And there are really two ways of thinking about this. It was one of those little bit flip moments in my head where I started looking at this from a 180-degree point of view. Initially, I was thinking, this is a battery module, like a power supply module with a management processor. The other way of looking at it is that this is an Arduino with the most awesome onboard backup power system ever. So it has a spot for the ISS-rated cells. Those are the big rectangular things in there, which are actually cylinders. And on the bottom, I've got breakouts, Arduino style. So with this board, you could essentially have, in this dimension, an Arduino with onboard power management and batteries and PV input and everything. So I want to use those just for my own projects, stuff for the ArduSat stuff. I want to combine that with one of these prototyping modules, and you've essentially got a self-contained, self-powered Arduino with a ridiculous amount of prototyping area. So some of the questions that I get all the time when I'm talking to people about this. This is probably the number one question. So how do you go with regular parts put out into space? Now the thing is that most people have the wrong way of thinking about this. It's not a matter of space being really, really cold, because there kind of isn't anything much there. The issue is more, how do you move heat around? If you have a computer which is using power from the batteries, it's going to be emitting heat. It has to go somewhere. On our normal computers, heat can go elsewhere by conduction. It can travel through physical structure. It can go via convection, for example, air currents. So the fans move heat off into the atmosphere. Or it can happen by radiation. And that's really the only option that you have for a satellite, because there's no other way for the heat to get out. So what happens is that when the satellite is in direct sunlight, it'll be heating up because the sun is heating it up. There is nowhere for the heat to go other than radiating out. When it's on the dark side, it will be radiating, and it's probably going to get really, really cold. So the general temperature profile of a CubeSat, because it's very small and there's usually good thermal conduction within the structure, you can model it as if it's a single point. Like the standard model for it is basically a 10 centimeter steel plate in orbit. And if you run the model on that, the temperature cycles between around -30, -40 degrees to about +85. Now satellites orbit, in low Earth orbit, take around 90-ish minutes for an orbit. So imagine that your electronics is being slammed down to -40 degrees back to +85 every 90 minutes. And that's basically the thermal stress that the structure has to go through. Now those limits happen to be pretty close to standard industrial parts. So you don't even really have to go to mil-spec parts for the most part. The other thing is, what about radiation? Turns out this matters less than you expect for a low Earth orbit satellite, because it still has a fair degree of protection. And it's only going to last a few months. If we were putting up something we wanted to live for 20 years, then you would use radiation-hardened parts and various other things. But for this sort of mission, it's not worth the trouble. And there are a lot of satellites going up now with just regular off-the-shelf parts. Another question I get all the time, in fact I got this just as we were walking into the room, is how do you talk to it? And a lot of people say, do NASA let you use their gear to talk to the satellite? Well, no, you're on your own. So, and this is a problem that is faced by pretty much anybody that puts up a CubeSat. How do you talk to it? And the thing is, it's moving very fast, so you only actually have it in your field of view for minutes at a time. And this is a really interesting area, and I'm actually just in the process now of looking at getting in my amateur radio license, because I want to learn more about this sort of topic. But there is a project going on to build a collaborative ground station network consisting of receivers distributed around the world, connected to the internet. So as a satellite passes across, it's a bit like cell towers for a cell phone network. It passes from one to the next, and you can get communication through the different teams. Another question is, how do you steer it? So there are 4 different ways typically that you can move a CubeSat around. In the case of FitSat-1, which is the satellite that blinks in space, all I did was stick big magnets in it, and that just keeps it aligned with the Earth's magnetic field. Very simple, it's like a big compass. You can also use magnetorquers. A magnetorque basically is a coil. So you can think of it as half a motor that reacts, instead of reacting against a fixed magnet or a spinning magnet, it reacts against the Earth's magnetic field. Typically what you use is 3 coils for 3 axes, which are embedded most commonly within the solar cells. And using a magnetorquer, you can basically reorient the satellite any way you like with about ±5 degrees pointing accuracy. Other methods are reaction wheels and reaction thrusters. One of the limitations is that they really don't like you putting explosive or high energy material inside the satellite when it goes up. And just recently I came across this. I apologise for the poor photo. It was the only one I could find. I thought this was a really clever idea. This is a project being undertaken by a company called Tethers Unlimited, and what they do is send up a cube, I don't think they've flown one yet, but this is a prototype, which has water in it. They then use power from solar to electrolyse the water and generate fuel, and they can get around 300 newton seconds of thrust per 100 grams of water. So the idea with this module is that you can integrate this with a CubeSat, and you've got essentially a 2U satellite with thrust control. And by their calculations, if they can get 700 grams of water into this structure, that will give them enough delta V to take a CubeSat into lunar orbit. That would be a project worth following. So, ArduSat 1, the hardware is coming together. It is now set for a launch on July 15. It will be going up on an H-2B lifter taken up by JAXA, the Japanese Space Agency, on mission HTV-4, which is a resupply mission to the ISS. And it'll be deployed using that mechanism I showed you earlier. And what happens beyond that? ArduSat 1 plus N. ArduSat 2 has, just a couple of days ago, was booked. It's now scheduled for an October launch. ArduSat 3 is already being discussed. And for me personally, what I would like to do is progressively open source the stack. As I said earlier, 2/3 of that volume is commercial off-the-shelf parts. I want to be able to progressively replace things like the flight computer, the power supply module, but I don't want to bite off more than I can chew. So for ArduSat 1, it's the payload. That's it. It's as open as can be, but the rest of it is commercial parts. So I'm going to progressively keep working through and collaborating, hopefully, with other folks. B-Dale.
Thanks to a hack we dreamed up for dealing with ITAR, you're probably about a year away from a completely open source the rest of the CubeSat.
Fantastic. Actually, on the subject of ITAR, something I should mention is that the reason that we have this problem now with satellite technology being controlled is that there was a satellite called Intelsat 1, which was being launched from China in 1996. And the rocket failed. Basically, it went over, crashed into a village, killed a bunch of people, which was very unfortunate. Not all of the rocket was recovered. Intelsat 1 contained some technology that was considered sensitive by the US government. So in 1999, they put a blanket ban on all launch and satellite-related technology. What happened subsequently was that the American share of the global satellite market plummeted from 83% to under 50%, and then they went, oh, damn. So on January 3rd, so just a couple of weeks ago, there was an amendment to the law signed into whatever it is, signed into law, which allows the president to exempt satellite technology on a case-by-case basis from the ITAR regulations. So hopefully that will start playing into this as well. And of course, my personal objective for this is I want to get cheap and open space tech into the hands of students and hobbyists everywhere. So, thank you. I think we're pretty tight on time. There may not be time for questions. Is there a minder in the room to...
Yeah, we'll just have one or two questions.
Okay. No hard questions, please. I'm tired now.
Hi, John. So there's a guy here in Canberra called Daniel Faber who's been playing around with CubeSats for a few years now. Mm-hmm. And one of the things he's doing is basically he's still using off-the-shelf components, but he's buying them in batches of like 100 or 1,000, and he's cherry-picking them for radiation tolerance. Does your project have any scope for doing that? Because that might extend the life of the device a bit.
Potentially, but that's something that would probably be done by the main ArduSat team. My scope on this is fairly limited to the parts of the payload that I'm working on designing. So, sorry, I couldn't answer that question. Looks like everybody wants to see Tridge, as they should. Keep going? Oh. Another question?
It's not setting up.
Okay, go for it. I'll move this out of the way.
Yeah, thanks. Your talk's much more.
No.